Hello, everyone, and welcome to Lab Manager's Ask the Expert webinar series. My name is Mary Beth DiDonna, and I'll be moderating today's discussion, Reducing Aerosolized Pathogens and PM2.5, Improving the Air We Breathe. We like our webinars to be very interactive, so we encourage you to submit your questions to us at any point during today's webinar. Our speaker will address these questions during the question and answer session following his presentation. To ask a question, simply type your query into the question box, which is located on the right-hand side of your screen. We'll try to address as many questions as possible during our time together. If we happen to run out of time, I will forward any unanswered questions to today's speaker, and he can respond to you directly if possible. Additional resources for today's presentation are also located on the right-hand side of your screen. I'd like to remind you that this webinar recording will be available for free on demand shortly following this presentation. I would especially like to thank our lab for sponsoring this event. This support allows Lab Manager to keep these webinars free of charge for our readers. So with that, I'd like to introduce our presenter for today's webinar. Jesse Coro is Lab's Director of Growth and Strategic Initiatives with over 15 years of experience in molecular and particulate filtration and energy reduction for multiple industries, including education, manufacturing, pharmaceutical, cannabis, forensic, flavorist, and government. Jesse is passionate about safety, and those who have had the opportunity to work with him or participate in his training sessions have experienced that passion firsthand. Jesse leads a group of dedicated safety professionals who share his passion and understand real-world business concerns while finding creative, effective, and affordable solutions that benefit both workers and employers. Jesse, thank you for joining us today.
Good afternoon, and thank you, Mary Beth. Again, my name is Jesse Coro with Lab. For over 53 years, we have been providing protection for personnel through filtration, protecting the air they breathe. Today, we're going to specifically discuss how to mitigate the risk of aerosolized pathogens while improving indoor air quality, which is called IAQ, a course for today's challenges in tomorrow's well-being. The product we're going to specifically be discussing today is the Halo, which is a ceiling-mounted air filtration system or virus mitigation system. I want to talk with you a little bit about how the virus is spread. When we were first dealing with COVID-19, one of the concerns was obviously social distancing and contact transfer. We were very concerned about touching surfaces and then, of course, touching our eyes, nose, or mouth. While that is still a concern, the major risk of transmission is actually through the air. So how does that occur? Well, obviously, if we sneeze, cough, or unfortunately, even if we go to the bathroom, we release infected droplets. Those droplets, when released from our mouth, are about 5 micron or larger in size. Put that in perspective, a piece of hair is about 10 microns in size. So the droplets are still extremely small. However, they are heavy. So they end up dropping to the ground and therefore dropping to surfaces and creating an infection source on the surface. However, these droplets actually desiccate. And when they desiccate over time, they end up becoming droplet nuclei. And these droplet nuclei range in size from 0.129 micron to about 5 micron in size. And when they become droplet nuclei, they remain suspended in the air for up to 4 to 16 hours. When they remain suspended in the air, and because the droplets are so small, we inhale them very easily. Our mucous membranes are not able to filter out microns of this size. So we have to figure out a way to mitigate the risk, again, of aerosolized transmission, capturing these droplet nuclei at the source and pulling them away from the breathing zone. The equation for infection is exposure to virus times time. So we really need to figure out a way to capture these aerosolized pathogens, again, droplet nuclei, in a very efficient manner. So how do we reduce the viral load and time the virus remains in the air? Well, there's many products out in the market today that are promoting 99.995% efficiency at killing the virus. Let's run through them a little bit because these are what I call placebo products. And I want to ensure that when we're looking at a mitigation plan, we're not fooled by some of the claims that are provided. So I want to start with UVC lighting. The problem with UVC lighting is it's certainly not going to decontaminate air. The efficiency of the UVC is at point of contamination. So essentially, the UVC light has to shine directly on the surface in which it's looking to decontaminate. In addition to that, UVC provides harmful wavelengths that can cause serious damage to skin and eyes. And the time to kill, which is called kill rate, ranges from 10 to 30 minutes. So it's not a quick kill like many of them promote. It still takes time to kill the virus, even on a surface. And importantly, it does not clean the air, so we're not reducing the risk of aerosolized transmission. It will reduce the risk, again, of surface transmission in a very controlled environment. Let's talk also about floor-mounted filtered units. There's many false claims about the product's efficiency. A lot of these companies are saying, take my product, plug it in the wall, it's going to process 500 cubic feet a minute, it's going to provide efficiency within a room of 1,000 square feet at 99.995% efficiency. Unfortunately, that's a very falsified claim, and I'm going to talk about that in a moment. But let's also talk about the airflow. The airflow of these floor-mounted systems takes the contaminated air down past the breathing zone. So remember, those droplet nuclei remain suspended up in the air. We don't want to drive those down. We want to drive those up and away from the breathing zone. So a floor-mounted system, while it has many different flaws, the biggest flaw is taking that air down and then, again, driving it past the breathing zone. In addition, it creates ground disruption and air turbulence, and the rated filters, or the rated HEPA filters, are extremely questionable. They're not medical grade filters. In fact, they're about an inch, maybe an inch and a quarter thick. That's not going to provide the efficiency that we need to capture the virus. But let's talk about, again, the product's efficiency. The claim of 99.995% efficiency, even if they use a medical grade HEPA filter in the unit, there is no possible way, there's nothing out there that's going to decontaminate the space or the air at 99.995% efficiency. What it may do is, once it actually drives the pathogenic particles down past the breathing zone again and to the filter may be 99.995% efficiency, and that's questionable, but actually the overall effectiveness of taking that air down is a whole different story, and that's the test results that are not shared. The next solution that many people are looking at is upgrading the building's HVAC, which is the heating, ventilation, and air conditioning system, to what's called MERV13 filters. What's the difference between MERV filters and HEPA filters? Well, it's the overall efficiency rating. So a MERV13 filter will be efficient at capturing potential viral particles, or particles at 0.1 micron, at about 50% efficiency. So even if we are able to upgrade the building's infrastructure to MERV13 filters, and most systems are not allowed to do the filter upgrades just because of the static pressure drop that happens, the fans within the HVAC system can't handle it. So more often than not, in order to upgrade to a MERV13 filter, as recommended by ASHRAE, they would have to upgrade their rooftop handling units, which is extremely cumbersome and expensive. And even if they do that, again, they're only going to be at about 50% efficiency, in addition to adding a tremendous amount of energy load on the building. And most importantly, this, like every other product we just mentioned, does not address room level mitigation. So basically, any infected pathogen that's driven up through the HVAC system is dispersed through the HVAC system until it actually gets to that MERV13 filter. So then there's reentrainment to other areas of the facility. Case in point, in a school, if you have a nurse's office and you have just your regular school, your lunch office or lunch facility, that air from the nurse's office to the lunch office is going to literally be the same air. So the people that are infected, whether it be with COVID or any other virus, that air is driven up and it's processed and it's passed through the HVAC system that travels in through the rest of the school. To me, it's not in a very effective way of capturing this virus or other viruses. And then there's also ionizer systems or dry hydrogen peroxide systems. And what this does is really, it disperses ionizers, positively or negatively charged, to rob the pathogen of its life-sustaining hydrogen. The problem with these systems are they're limited based on the needed airflow, so they don't work unless there's actually a fan dispersing these ions. And then there's a density factor of dispersed ions, which will determine the kill rate, which ranges from 60 to 30 minutes. And what do I mean by density factors? Basically, close to the ionizer, there'll be a greater density of ions that will have a greater impact at robbing the life-sustaining hydrogen of the viruses. The further you are away from the ionizer, obviously, the less efficient these ions become. And they only last, the ions, they only last about 60 seconds, so that you have to constantly generate the ions to be efficient. And some also generate ozone, which is extremely dangerous. So what is the solution? As I mentioned, we offer the Halo, which is a viral retentive air purifier. Again, we have focused on filtration for over 53 years. And what does this Halo do? Well, first, it provides room level mitigation. It captures viral particles and generalized pollutants called PM2.5, which we are going to discuss later on in the presentation. It captures it at the source. So basically, depending on the size of the room, will indicate how many halos we would require to provide extreme efficiency. The airflow pattern of the Halo, it takes dirty to clean airflow patterns up and away from the breathing zone. So again, those droplet nuclei that remain suspended in the air, this system actually drives it up and away, capturing these viruses in a medical grade H14 HEPA filter, which again, the filter provides efficiency at 99.995%. But then we have to look at the overall load concentration reduction. And this is what you see in the graph below the picture of the Halo. This was a testing done by a third-party source called 3Flow. And what we wanted to see is what happened when we had a load factor in a facility and what was the overall reduction. And that's the important key critical testing that needs to be performed in order to understand the overall true effectiveness of a filtered solution, which is called ventilation effectiveness. What we saw when we have load concentration in the baseline that you see from this chart is without the Halo, we have 896 million particles that were generated just from talking in a standard office. With 2 air exchange rates per hour. So the HVAC system was processing 2 air exchange rates per hour. So every hour it was processing air. Even at that, we were experiencing a load factor of 896 million particles. We put the Halo on and we saw a significant reduction of greater than 70%. So from 896 down to 253 million particles. That sounds like a lot of particles, but when we're talking 0.1 micron in size, it's really not a lot of particles. But that reduction significantly reduces the risk of aerosolized transmission because the quicker and more efficient we can take away that load concentration, that viral load concentration, obviously the more effective the product's going to be. And that's the key performance indicator. And of course, the improved ventilation effectiveness of greater than 20%, 27% from traditional HVAC. And what do I mean by that? That's not actually reduction of particles. That 27% is how much more efficient the room and the processing of air was when the Halo was on. So we drastically improved that effectiveness, again, greater than 27%, all without connecting to the building's infrastructure. These are free filtering systems. The only thing they're connected to is standard 110. The energy consumption is 50 watts, which is on estimated average about $1 per day. So again, you do not have to break into the building's HVAC system. So while it's not a simple, I'm going to get the unit, pull it out of the box and plug it in, you have to understand this is a commercial grade filtered solution that's going to provide you that load concentration factor that is critical to mitigating the risk. And this graph, this GIF is going to really show you what happens when somebody sneezes and how a virus spreads throughout the facility and goes through the HVAC system and can propagate and then infect other people in an area that the infected person was not in through the HVAC system, and what happens when the Halo's on and how we literally drive those pathogenic particles up and away from the breathing zone, again, drastically reducing the risk of transmission. Clean air, dirty air in, clean air out horizontally, which is what's called the Coionda effective airflow. So not only do we capture and then disperse clean air, but we also help, again, ventilation effectiveness by reducing what's called dead spots in the facility. So if an HVAC system is not working properly, there's dead spots. So there's going to be areas in that facility where you're going to actually have a greater load concentration because you just don't have the proper airflow. So the halo will also provide you a solution at reducing those dead spots. So I remember I mentioned PM2.5 earlier on in the presentation, and I did that for a purpose because it's critical in, obviously, again, providing solutions for today's challenges and tomorrow's challenges. So let's really talk about it and take a little deeper dive into exactly what PM2.5 is and what I call the unseen danger, because it is unseen. PM2.5 is combustion particles, organic compounds, and metals, viruses. It's pollutants that we are exposed to that we are not aware of because we can't see it. The only way we're aware of it is because we end up becoming sick. We end up having respiratory issues. We end up having heart issues. Strokes is a factor with PM2.5. So there's a lot of risk factors if we're exposed to too much PM2.5. And just to put it in perspective, again, human hair is 50 to 70 micron. I actually said 10 micron earlier, completely misspoke. Fine beach sand is 90 micron in size. Dust and pollen is 10 micron in size. So it puts it in perspective how small PM2.5 is. Inhalation of these particles, again, just like the virus, bypass the nose and throat and the mucous membrane and will penetrate deep into the lungs and attributes to chronic disease such as asthma, heart attack, bronchitis, and other respiratory illnesses. In fact, exposure to PM2.5 is linked to higher COVID-19 infection and mortality rates, and that's right from the NIH website. This is a real issue, and actually, some on the call or on the webinar may have heard of SBS, which is called sick building syndrome. And why do we get sick building syndrome? It's because our facilities are only as clean as the air outside. We're exposed to that, and now we're in a confined space continuously breathing that, and our health is at risk. Again, put this in a little bit of perspective. Back in 2015, there was a study performed on a 25-year trend of the global burden of disease and how it attributes to ambient air pollution. And then recently, Dr. Chan from Harvard wrote an article discussing air pollution and how it's linked to higher COVID-19 death rates. There's something to be said about that. So we have to figure out how to clean the pollutants. And the halo, again, efficiency, ventilation and filtration efficiency is going to work to clean up the air in general. Now, if we take it a step further and we look at the death rates that are linked to outdoor and household air pollution, you just look, I mean, these numbers are staggering. 7 million people die prematurely every year from air pollution, both household and outdoor, and household also meaning our work facilities. 34% of that, obviously, heart disease, 20% from stroke, 21% from pneumonia, so on and so forth. We have to come up with a solution to clean the air we breathe. And again, this is all we've been doing for 53 years, not just with the halo, but we've been providing filtered solutions for laboratories specifically, providing solutions so that they don't release potentially harmful PM2.5 and other pollutants to the atmosphere. So we understand how important this is. Some other graphs, the WHO says 30% of all new remodeled buildings suffer from sick building syndrome. The EPA, sick buildings cost the economy $12 billion annually in lost productivity. The cause of sick building syndrome: inadequate ventilation, inadequate humidity levels, airborne particulates, airborne chemical pollutants. I mean, it's all things that we have been preaching for many, many years. We cannot allow dilution to be pollution we generate, specifically in laboratories. And when I talk about laboratories, I'm specifically talking about fume hoods. And I say that because fume hoods generate some of the greatest pollution on the planet because it's constantly mixing chemicals and throwing them out into the atmosphere, hoping that dilution is going to take care of it. But unfortunately, it's drastically impacting us every day. So in summary, we must look at solutions that deal with today's issues, but also look forward to tomorrow's challenges. We're not just in it to come up with a solution for COVID-19, though we're glad we're able to. That's not what we're in business for. Filtration, when used appropriately, provides a significant impact to overall ventilation effectiveness, as we discussed, and reduces the risk of PM2.5 and overall viral load factors. And that's COVID-19, influenza A, B, rhinovirus, any virus that becomes aerosolized, which are many. While there are many options available and some that look appealing due to cost, we must look at all the data to determine the best solution for our facilities. And yes, I know cost is a driving factor, but please do your research. There's a lot of false claims. Pollution plays a significant role in the global burden of disease. Again, as we discussed, you go on Google for 10 minutes and you search PM2.5 and the effects of just COVID-19, and you will see a tremendous amount of data. This is also where filtration can contribute and benefit well beyond the halo, especially within the laboratory, as I discussed earlier. So with that, I thank you for your time, and I wanted to leave enough time for some questions and answers. Thank you.
Okay, great. Thanks very much, Jesse. So at this time, we're going to move into our audience question and answer session. So again, for those of you who may have joined us late in the call, you can send in your questions by typing them into the question box, which is located on the right-hand side of your screen. And if we do not get to your question today, it will be forwarded to our speaker and he can respond to you offline if possible. So Jesse, our first audience question is, what is the difference of a MERV 13 filter versus an H14 HEPA filter used in the halo?
Great question. So MERV 13 filter and HEPA filter differs in regards to the overall efficiency at capturing particles, specifically particles from 0.1 micron to 5 micron in size, where a MERV 13 has an average rating between 50 and 75%, or less than 75% if you look at some charts. As an H14 true HEPA filter provides efficiency at 99.995%. So it's really about the overall efficiency of the filter.
Okay, great. Thank you very much. So we have another audience question that says, what is the difference between an ionizer and a DHP system?
So an ionizer releases negatively and positively charged ions. And those ions will disperse to find a particle or a virus to, again, rob it of its hydrogen. And a dry hydrogen peroxide system will actually release dry hydrogen peroxide and provide a disinfectant agent within the room. The difference being an ionizer can be on when there's occupants in a room, and a dry hydrogen peroxide system cannot be. That room cannot be occupied, as it can be very hazardous to your health. So it does work, and it will disinfect surfaces within the room, but not the air. Whereas an ionizer will help to disinfect some airborne particles, but again, the ions itself must find the viral particles to do so.
Great, thanks very much. We have another audience question that is asking for more information about changing the filters in the halo.
Sure. So the HEPA filter will need to be replaced every 3 to 5 years, more often than not, probably every 5 years. And basically the halo itself will, the filter housing will drop down, and the HEPA filter is on a knife edge and gasket system where you can move the HEPA filter out very safely and then put the new HEPA filter in.
Great, thanks very much for that. We have another audience question that says, we have Airlab filtered ductless fume hoods with HEPA filters. Can we improve our air quality and filtration by keeping the hood sashes open all the time rather than closing them when the hood is not in use?
Absolutely. That's a great question for sure. It's the same HEPA filters that we use in the fume hoods as we use in the halo. So they are all H14 rated HEPA filters. And for sure, if that ductless fume hood is not being used for chemical use and you just want it to purify the air, it will absolutely do the same as the halo.
All right, great. Thanks very much. There's another question that says, is there any independent data on the effectiveness of needlepoint bipolarization in reducing viral ineffectiveness?
Viral ineffectiveness. There is data. There's a lot of data in regards to ionizers as well as UVC, and we can certainly take that offline, and I can provide you with some of that independent test data. Thank you for the question.
Great. Thanks very much, Jesse. We have another question that asks, how do you test for viral load in the air with your equipment?
So it would have to be done with a surrogate COVID sample, usually MR2, MS2, and obviously in a very controlled environment. And we would look at the overall load factor before the halo's on and then the overall reduction after. We could also do surface sampling as well. So there's a number of different ways to test the overall viral load factor and the efficiency of the product.
Thank you. We have another question that says, what is the effective coverage area for the halo?
About 3,000 cubic feet of space, and that will provide an additional 3 air exchange rates per hour. So depending on the size of the facility and the facility in general, will determine how many halos will be required to provide true overall efficiency and ventilation effectiveness.
Okay, great, thank you. We have another question that says, does the halo system have a separate fan unit?
The halo system is the fan unit. So again, it's independent from the HVAC system, and it will run on its own fan and filtered system. And I want to quickly elaborate a little bit more on that question previous to that question regarding the cubic feet of air, processed air that the halo is efficient. We have to be careful because I know there's a lot of systems out there that says we can process 1,000 square feet, with these floor-mounted HEPA systems. Again, a falsified claim. We have to look at ventilation effectiveness, and it's critical. And while many may look at their facility and say, wow, that would be a lot of halos that are required. Yes, but we have to understand what we're dealing with here. We're dealing with a virus, a very deadly virus. And unfortunately, I don't think it's the last to come. So we have to look at what we're actually looking to capture here. So I just want to touch on that a bit because I do know when you start running the calculations, it may get overwhelming. But if there's any more questions related to your facility layout, I will be happy to work with you and design and engineer where it would be appropriate to place the halos.
Okay, great. Thanks very much. We have time for one final audience question, and that is, what would you recommend for a situation where there are aerosol generating procedures such as dental treatment?
Well, I would recommend certainly a filtered solution. Obviously, we'd want to take that air upwards. And again, the driving factor is we don't want to take it down past the breathing zone of the doctor or the patient. So we want to drive those aerosolized particles that are generated from treatment such as dental activity up and away, and that's where I would recommend a filtered system. Again, we have to look at this as a multi-tiered approach. This is one piece of the puzzle to providing a solution to mitigate the risk. So I'm not saying that the halo is the only solution necessary, but it is certainly a significant factor. Thank you for all your questions. I certainly appreciate it.
Okay, great. Thanks very much, Jesse. So this brings us to the end of today's webinar, and I would just like to remind our audience that this webinar will be available for free on-demand download shortly following this live presentation. So please keep an eye on your email inbox for that information. So on behalf of Lab Manager, I'd like to thank Jesse Coro for all of the hard work he put into his presentation, and thank you to all of you for taking time out of your busy schedules to join us today. I'd also like to extend a special thank you to our webinar sponsor, Lab, for their support. For more information on all of our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you and have a great day.